Anche qua vengono.
Okay, you can.
So I'm very happy to do this presentation now because I have the opportunity to reset your brain after the fantastic fluidodynamic lesson that we listed before. So the aim of my presentation is to introduce you the Sailor E2A3A observatory site in the Adriatic Sea, of course. So I do this preparation job for my colleagues that will go further in the details of the background scientific teams. And I will give you a general overview of the site architecture. And of the reasons because we can consider the data coming from the site as representative for a basin scale, not only a local scale, but also in the South Adriatic basin scale. So, first of all, the site is located in the center, approximately in the center of the Southern Adriatic Sea, about 60 nautical miles off the Bari coast, at a depth of 1185 meters. And it consists of two independent moorings. A primary mooring that is a surface buoy that is equipped with photovoltaic panels for the energy and a weather station with radiometers, physical and biochemical sensors at the surface and at the mixed layer of 15 meters. The core of the system is a digital control system that manages the data acquisition, the power, monitor the status of the sensors, and also manage the telemetry. The secondary mooring is located about 1 mile from the primary, of course, for safety reasons, and it's basically an instrumented mooring line with different physical and biochemical sensors at the different levels. And also, from a few years, two sediment traps in collaboration with the CNR. About the telemetry, both the mooring are equipped with the positioning system, satellite positioning system, GPS and iridium beacon. The primary mooring, of course, has also a two-way communication system with the satellite global star chain to transmit the data in near real time on the ground. The secondary mooring is equipped with two-position iridium beacon for safety reasons in case of unwanted surfacing of the mooring, of course. We can monitor it. The site is part of a national and international networks and programs, as you can see here. Recently, we are trying to join to the EMSO. So, basically, this is the most important question. Why this site?
Are the two rings connected? Or
not connected, no. We have the surface buoy that is acquiring and transmitting in near real time data. And the mooring is, the data from the mooring are downloaded when we do the maintenance, in the average 1 time per year.
They are very far? 1
mile, about 1 mile, just for safety reasons, because the surface buoy has 1,500 meters of radius of circulation in the surface. So you must stay at a correct distance to get this kind of situations. Of course, why this site? Because why in this area? Basically, because this area, it stays in the center of the South Adriatic Pit, is an area with a quasi-permanent cyclonic structure, strongly influenced by atmospheric forcing. It's a site of deep convection processes, and is one of the main, or maybe the main deep water formation site in the Eastern Mediterranean. And moreover, it has exchanges with the Ionian Sea by the Otranto Sea. Why this site? Because we can study many processes here, physical processes. As you can see here, they have been studied already, but they are still under study. And the products primary products of the site are long time series that are useful, that are the base for the studying of long-term characterization of South Adriatic Sea. changes in response to climate forcing. So there are good reasons because we chose that position for the site. Long-time series, of course, are a key factor in understanding climatic trends, oceanic processes at different time scales. Also for understanding the low-frequency oceanic variability. And basically, they are the only means available that can resolve high-frequency processes. And we, since 2006, have the SADR 8238 site that monitor the South Adriatic region. This is an example of our long time series. You can see imposed on the plots also the Gantt plot. That lines are the lines of the actual acquisition we made with these instruments. We have some holes due to the maintenance or period of not working of the buoy. And this is actually the longest time series available in this region. Yeah, having a look to the site architecture, this is the primary mooring, the surface buoy. The available measurements that we have from this buoy are time series. And we try to put instruments, install instruments, in this case the meteorological and solar radiation, to study the RC interaction, surface properties. We have CTD and with the dissolvent oxygen sensor at 2 meters and 15 meters. And also we have 2 sensors for the study of the carbonate system, also at the surface. As a supplement to this time series, we have also a long time series of oceanographic cruises data, CTD data, along some historical transect. We have also glider data and floats data that my colleague will show you later. These are part of the stations that we repeat each year from 1995. And these are examples of the average time series of the principal parameters. Okay, just summarizing the table for the parameters that we collect, the relative depth and height above the sea level, and of course the sampling interval. You can see that it's a very high frequency interval. The satellite transmission of the data happen each 3 hours, and we have a continuous data transmission from September 2014. The secondary mooring, it's, as I told before, is a moored line, an instrumented line. Also here we have a time series of ADCP current profiles for the upper layer. We have several CTDs to try to study across for example, the Levantine intermediate water depth, the outflow level from autumn to sea depth, and also, of course, to study the circulation and properties in the deep layers. And we also have, as I told you, 2 sediment traps, one in the euphotic zone and the other at the bottom. This is the Gantt plot for the data availability, upgraded to not to the last cruise, of course, because it's still under variation. And this is the summary table for the parameters we collect with the mooring. Okay, data cycle. The data are in the real-time data are transmitted with the satellite to the ground, where we submit the data to many quality control procedures, and then we send the data to FTP server and also to National Oceanographic Data Center at UBS and to Copernicus, of course. With the delayed mode data, we do the maintenance once per year, in the average, and then the data downloaded are put inside the same cycle and are available in the different data sets. For the near real time, the Nettuno server, of course, is one of the database we use, but also the Mongoose and MyOcean database. And for the delayed mode, also to the NLDC. We have also a web page where you can see in form of daily panels the meteorological and oceanographical data, and also a panel with the 10 days time series shown and refreshed each day, of course. We also have the archive for near real-time data on monthly base. And also for the delayed mode, you can find and download data from the long time series parameters we collect, also the current data, of course. Okay, we submit the instruments to many quality control procedure. We do calibration after each recovery and before each deployment. We use to do calibrations. You visited yesterday our CTMO, the Centro di Taratura, here at OGS. And we submit the instrument to checks and inspection following the best practice handbook made in the framework of FIXO3 project. For the data, we refer to different manuals that are the RIT Marion and Ocean Sites manuals for the real-time data, and the Med Atlas CDataNet quality control manual for delayed mode data. Okay, trying to answer to the title of this presentation, why we can consider this data as representative. Because basically, first of all, we do, of course, the post-processing on the time series data. We clean and spike them, this data. We apply a low-pass filter to obtain inertial non-tidal flow. And we have, of course, a time series in the form of averaged hourly data, finally. We validate comparing this data with in situ CTD measurements carried out in several places in South Adriatic region, as I told before, with CTD data. That are, of course, the CTD are calibrated here, usually. We have very high accuracy for temperature and salinity and dissolved oxygen. And we studied also, we made a lot of studies in the past. One of these is Benzi et al. 2014. We calculated the correlation coefficients between these data sets, and we saw that the correlation coefficients at the distance of about 45 kilometers from the site are very high and decrease a little at the distance of about 70 kilometers. So this means that we can consider our data as representative for the open ocean processes in the Southern Adriatic. Also, we have also, of course, salinity samples, discrete salinity samples collected during the cruises that we measure here in the very precise laboratory salinometer with high accuracies. And also, we check the instruments each time we do the maintenance, the recovery of the instruments. We do a simultaneous test with the instruments installed on the carousel of the CTD.
3 minuti.
Okay. Adesso erano 3. Quindi, we attach the instrument to the carousel and do a test for at least 1 hour, and this is the result. And just to be sure that and to quantify the eventual drift of the instruments with respect to the CTD that is more accurate. We did also, Stefan here, did this job that is comparing with the numerical model, the MIT GCM model that was calibrated for the Southern Adriatic Sea. This is an example of the comparison between the two data sets, and as you can see, there is a quite good correlation. And we saw that this experimental modeling integration approach enabled to a better understanding, not only of the local dynamics, but from the model results, we can infer also information about the general oceanographic characteristics. Last but not least, we did also work on the comparison between the ERA interim data server archive from ACMWF at step 0. So with the data acquired at analysis made at 0, 6, 12, and 18 UTC time in a region that is the region inside the red square. And we averaged only our time series just to compare them, the same, and submitted them to a quantitative statistical analysis. You can see in the table here very high correlation coefficients, and this is the results. These are the results, the plots of the two series overimposed. As you can see, there is a very good correlation, and of course, also this. Study tell us that we can consider our meteorological and surface data as representative at a certain degree of accuracy of the entire basin region. I'm inside the 3 minutes. Okay. We are these guys. Thank you. I suppose no questions.
Thank you.
I suppose no questions about the picture.
I have a question.
Yes, please, good question.
You are thinking about like to doing an integrated mooring site, like connecting both and trying to transmit from
Yes, we tried in
from
the
the
past.
secondary to the primary and have near real time mooring.
We have this opportunity. We have acoustic devices, LinkWest, that we tried in the past to install, but we had some problems. If I don't remember that, the problems were related to the ADCP data. It's a lot of a huge quantity of data.
Yeah.
So this was disturbing the acoustic transmission. So we decided to stop the experiment, but we are waiting for the next future and some funds for some again this transmission. This is the intention, of course.
One of the goals of the passing to EMSO, to the new program platform, is to have a work together with the NGV. They are very specialist in the data transmission and communication among the two systems. So there is an idea to work on that, to make all data available in real time. One of the things that we could just change and make it an inductive cable, to make it more easy, but it's very expensive. We have so much expenses in that, and we have to see how it will be financed.
If I understand, you only have one ADCP on the line, mooring?
Yeah, and we have a punctual Seaguard current meter acoustic at the bottom, but it's just point.
There is a lot of portion of the water column where you don't have velocity data.
Sorry?
There is a lot of water column.
Yeah, we have only the upper layer because we have the ADCP is installed at 300 meters about up when looking, and so we just have the information for the upper layer, 300 meters, and then some information on the bottom. Only that, yes. But
we submit recently a project, and where we hope the fund it will be funded. So in this case, we want to, but we'll put the promise to buy the new Nortec, to buy
cover all the
have a range of 1,000 meters, and there was also you can make it different for the frequency, so you can be more specific in one area and then diversify to another area, and then we will want to put below the ADCP, and then we could cover the whole water column.
How important is this no sample layer in terms of circulation in the Adriatic Sea? Good question.
Which
Yes.
one? Which one was which layer you're referring?
From 300 to the bottom, you
This is
did not
very
sample
important.
that, so
This is
it's
very
important.
important.
in
This
terms
is
of
very
circulation,
layer,
for you,
also
very
for
important.
biological.
It's
Yeah,
very
it's
important,
a
of
point
course,
of view,
but
you lose
you have to
completely the-
consider the story of this mooring, this site. So in the time we started with a few instruments, CTD mainly,
Yeah.
and one current meter. And in time we, with many projects, try to implement and upgrade the system.
It's good, huh?
At the moment, it's very, very difficult to recover the mooring line, the surface line and mooring line, because of course you have lots of instruments. You need a big ship to do this job. We did also with the fish boat, of course, that because but it's not so simple. So before you upgrade the system, you must consider also this kind of problems. And recovery deployments.
Well, how long you deploy? What's the turnaround timing?
It's
A
8
year?
to 10 months, depending on the availability of the ships, of course. In the average, once per year.
Once.
it goes. Sometimes we went also 2 or 3 times for the surface buoy only. Recover it and deploy it again for problems of instruments and so on, but basically 1 per year.
And just to finish, we're connected to the what I'm because I'm following the presentation from Pepe. About how important is the data that we're missing in the intermediate water. And also we have seen from the analysis that we did in the paper with Laura, that we are missing the other part, at least until 500 meters, where we believe that is the migration of the zooplankton. Because we're the signal, but since we do not have the data, we have that have been interrupted. So it's very important. So also the layer between 300 and 700 meters is the layer where the 11 centimeter water is flowing, and it's very important to measure. We will see there are some signals at the bottom that we will try to explain. We just recovered, but we don't know exactly. It would have been very useful to have the ADCP in there to get more hints of what was happening. So I will.
Are you gonna repeat this correlation what Pepe showed? Because I have some questions.
No, which correlations?
The ECMW data and this.
You can do these questions to Vanessa.
But only if she repeats these figures. Are you going-
I don't have the figures here.
He will give it to me.
No, I destroyed them.
we can make it later. Finish to see.
Later.
What is your question? Yes, we can.
No, I know. I would like to see the pictures because he just skipped over.
There
I
was
will send you by email.
There was to demonstrate that the data that we are using and measuring in the Southern Adriatic are really fit well with the ACMWF data.
Okay,
Yeah,
yeah. This
in
is
this
what
case.
I went in some details, but no, I don't want to take your time.
Okay, so we finish and then we can discuss in this. Okay?
We are next to one office next to the other.
Yeah. So I will try to summarize, give a hint more for people that know about our observation side. So now we have more than a decade of the high resolution measurements. This, as Pepe said, is the highest, the longest open sea time series in the Adriatic Sea. I don't have to repeat it, but here is a specimen for our friend from Mexico. It's quite different when you talk about we are very coastal. You said yesterday it's more around 60 miles from the coast. In 60 miles from the coast, we're already in the here in the. Oh, what is this? What's happening? I finished the presentation. Okay. So in here. Yeah. So in 60, this is more or less the distance between the coast and the position of the observatory is 60 nautical miles.
Mm.
So, and we say open sea.
Yeah.
So, as I say, everything is relative and depends on how we see it, and also the Rossby Reclamation, everything is different in this case. So it's the deepest part of the Adriatic Sea. There is a strong influence of atmospheric force, and here is the area where you have the northeast. We have the Bora. The Bora, there is a dry. It's coming from east, not east, very intense, and it's not steady, but comes in as sparse. Okay, and it is the site of the Adriatic deep water formation here. Pepe also mentioned there are several processes to study. We have studied the deep water formation. So in the center of the peak here, we have the cascading. Here is the Gulf of Bari, the Canyon of Bari, excuse me. And where all the two moorings in the area for the two moorings that the CNR has. So we have, now we are thinking like a joint area, not having the, because both sides are relatively connected, but big processes. Because we are affected what is happening also in the water flowing in the canyon. We have also the mesoscale variability, and we are now measuring acidification. And since we are here, we have the exchange among the Adriatic and the Ionian Sea. This is our observatory, and one of the questions, not to repeat, is just the whole area, the whole Adriatic Sea is since it's a semi-enclosed sea, is the question of the heat and content salt change. So the heat in the salt content is very directly influenced by the circulation in the Adriatic Sea. Here we have this is the Otranto, the level time water comma, and the layer in the middle. We have also the surface layer that is entering from the in the eastern side. We have a cyclonic circulation, a complex cyclonic circulation, but the water is flowing here. Part of this is remaining in the area embedded in the cyclonic circulation. Then part of it flows up in the northern Adriatic. This is a shallow shelf. And then this is the water form here. So it is strictly related of the circulation of the basins. So it depends on the characteristic of the Levantine intermediate water or the kind of water that is entering into the basin that will give the amount of salt and heat for the whole Adriatic Sea. Then the other thing is that very influencing is the North Adriatic, the formation of the North Adriatic deep water, and also the tide, how dense it is, and this is also depending on how much salt comes into the okay. It depends enter here in the characteristic of the water and the volume of the Adriatic deep water form in the north that flows downwards. Again, the heat fluxes, because the interaction, air-sea interaction, and will give you the amount of salt and the content in the area. So, as we said, we have the premoline characteristic. This is the whole time series from November 2006 till we recovered the data, the moorings in October this year. We just came back after when we came from Mexico. So we have only this have 10 months of lag data because we recover the whole system and then we have to put it back in the water. One of the things is that, as you can see, we have a very strong variability, and that is happening. And we have you cannot maybe not see well the blue lines. The blue lines at 300. The blue line is the 320 meters. The green 540. The red is 730. 900 is this bluette, and then this here. The Violet is 1,000, and this one is at the bottom. So we can see that there has been increase. There has been a decrease of salinity in the intermediate layer in the first years of the mooring, the time series, and we have an increase of this. So we can divide the whole period of measure. This is 11, 12 years of measurements. We can divide it into and we can refer this, what is happening, as I said, directly into the Ionian, because the water, as I said, entering in the Adriatic Sea is really influencing the whole system. In this case, we have the water. We have anticyclonic circulation in the Ionian Sea. So the water entering from here, this is for you, there is not more. The water flowing in the surface, this is Atlantic water, is less saline and less warm, okay? And then flows, in this case, is embedded in this anticyclonic circulation and goes directly and enter into the Adriatic Sea. In this case, so the saline water here is very saline, okay? We have the Levantine water has the path is more preferential, flowing directly to the Sicily Channel. This is what we call the bios, or bios, how we want to say, miros, we said bios, yeah. And one is one of the architects of this theory, and that we have. And so in this case, it means the oscillation between the Adriatic and the Ionian system. In the other side here, as we can see, and it's really related, we have in cyclonic mode in the Ionian Sea. So the water is already embedded in this circulation. The Levantine waters is going directly into the Adriatic Sea. So in this case, we will have the more influences of saline water. The less saline water is flowing to the Levantine Sea. Okay, so this is more roughly to explain the circulation. So for this, we can see in here the Hofmüller diagram. We can see the influence. This is potential temperature. We have entering since 2014, maybe 13, is entering very saline water. This is Hofmüller from the data from the mooring. So in this case, we have a high frequencies resolution, but we have less resolution in space. Okay. We have, but the signal, we have a very good signal for the water entering, very core of high saline water entering now is affected until 800 meters almost. Here we have a very low salinity. If we compare, so we said, with the other data that Pepe shows, there is for the in this 1 by 1 degrees from the CTD, from the cruises. So we have a high resolution in depth, but not in time, because we are doing 1 or 2 these cruises during the per year. Okay, but at the same time, we can see almost the same pattern. The one thing is that it is here that we lose the at least the signal of we have a less high salinity intrusion. We have to see that here in this case we have for each cruise we made the average of all the salinity profiles or all the CTD profiles to get one profile. So we have salinities from here that is very saline with those that is less saline here. So maybe in this case we can smooth the profile. And we are losing in the other one, we didn't get this low salinity in freshwater water masses. So what next? So that is the recent thermoline circulations to get what is happening now. We recovered we have the cruise in the Adriatic Sea in October. So we recovered the time series, the last time series. And this is what we have now from 2017 to 2018. And here maybe you can see much better the time series. So we can see here as a feature, okay, in this we can see that there was a convection in 2018, a very clear convection. Then we have that is very clear to see that is a two-layer system. Okay, in this case, okay, we don't have we didn't probably have the time to see the data also from 120 meters, but from 350 till 750, they have some characteristic. And then we have this second layer. And this is second layer, something that is never had before, is that we have now these high oscillations. And then that happens during the springtime. During the springtime, we have is the in concomitance with the arrival of the North Adriatic dense water. So we have it here, and the same at less during 2018. This is 17, and that is 2018. What we have, the next step that we want to do it is to verify how much water is was formed in the north, and to see also with the data from maybe from the moorings that you recover now, how much water it was, what was also the velocity of these waters flowing southward in the canyon. This is the density field variability. So there is again we have the dense signal of the dense water convection. We have a general trend of the increase in density during in this period. We have a year generally is increasing, and but we have what is mentioned is that we're really in January during the winter is late winter, April, spring. We have this jump in the first two time series, that is 350 and 550 meters, that we have this jump of intensity. Okay, this is the current field, a snapshot just for 70 meters. We can see this is strong barotropically. And
these are the upper layer?
This is from 200 meters. This is 200 meters to 270
Sorry,
meters.
I didn't have to put that.
Okay, maybe it will be better. Yeah, this is a nice snapshot from 200 to 270. So, but still here you can see there is a lot of reversals of the circulation. There is very high variability. These are just the data we just recovered. This is the first. We just processed, get information. That's it. We haven't done anything much. During the cruise, we also did the CTDs. We have the transect, and we have here for the half of the whole transect. But as we said, you have with the African countries, we have a problem with our neighbors in Croatia that we are not able to sample. Even if you take a 1 day more, we are not able to sample anything. We have problems. So we will try to manage in another way. And this is this graph. Right. In this graph, we can see here. We also extended to the A2M38. This is I thank Catalina Vedana for this graph, and here all the results. What is really the first what we were very interested is to see, and this characteristic, and well, there was a certification here. And we have a pool homogenized water still here. So this kind of graph we expected to have a late spring when it was after the convection, and we will have this when the start of the stratification. but it was in October and they were still here. So we also find something interesting is that here we have this like a signal of turbidity, something flowing down, and we have something that is new, is the high core of salinity here on the western coast, here toward the coast. We never have it this year because the more salinized part is in this area. So one of the explanations we are saying that the cyclonic circulation in the area of the pit was very strong, that really isolated the center of the pit. So we will have to get to more information to see the horizontal maps, maybe from satellite or the ADT, to get an explanation for this. So this is just to see 2 or 3 things. We have transit processes in the Adriatic Sea. We have found here, this is for a snapshot for the 2006-2013. You can see this, and then we have this down, and then again start going up. So at the beginning we were saying that there was a trend. It's a drifted in the instrument, but couldn't be because we very much. I put it for myself, you see. And then Markfor's instrument, no, because we tested the instruments and things, and then we cannot ascribe it to open ocean convection because it is just fixed in one thing, place. And there was no convection until the end, until the 2,200 meters, even not 100 but was not 100, 2,000 meters, never reached in the last 20 years. So one of the explanations is, is this paper that we wrote with Stefano, and this is that we have a sawtooth modulation of the bottom. Then we have the phase here that was a slowly continuous mixing process, and then I won't go into detail. This is a cyclonic circulation, analyzed for 2 days difference, and then we have here then the sudden intrusion of the North Adriatic episode that increased the potential density. So, and maybe I'm just running out of time, and so maybe what things we can talk later.
Excuse me, the previous slide, this one. No, nothing.
Okay.
This is density or temperature?
Temperature.
Temperature. Oh, okay.
Yeah. And then, okay. So another thing is that we can, from the data we have here discovered for another snapshot, and for 3 months we could see the passage of cyclonic eddies, but we have cyclonic eddies in the intermediate ledges with an anticyclonic eddy at the bottom. So it's treated. We have this. As I said, if we could have the IDCP measurements, it would have been better for the whole here. And there have been a lot of publications from the sites, so we are not only an operational observatory, but we are working also in science, and these are part of the papers that we are working with the data, writing for the data that we are obtaining in the area. Thank you.
Questions?
Yeah. And about this trend, not the last one, like few slides before.
For the what we have now?
No, the other plots before that you said that there was quite a lot of variability on the.
This year? The oscillations.
The other still on temperature.
This year?
Well, it can be this one, yeah. But was another one, but but you're talking about what's that 0.1 degrees of, well, this is salinity.
This is salinity.
Yeah,
but if you have salinity and you have
yeah, well, I mean it's 0.05 oscillations of 0.05 PSU, and on temperature you got 0.0 degrees of temperature. Oscillations, there were very small oscillations on the other plot.
In general plot, the total.
The total?
No.
The total, okay.
Yeah, at the beginning.
Okay, this is for the long time series. So
yeah. So my question is, if
this year,
for example, you see that it's 0.1 PSU of variability or
Well, if you see here, we have
38.7,
38.7, you have here, and then here you have 38.85.
Yeah, it's 0.15
Yes.
PSU. It's a very small. I mean, what I mean it's a small.
But for us it's very high. For us it's very high.
Where on this timeline, where is your calibration center start? On this timeline, the calibration center, because you're looking at very fine scale, like maybe temperature and salinity oscillations. So how you need a very precise light calibration. So where
Well,
all this time series, all this it has these calibrations.
Yeah.
All from since 2006.
Yes.
Yeah.
Yes.
That was my
And before the one of what we do is we check as Pepe showed, that we check with all the instruments we put together in the rosette, and we put it together also we download it with the 911 CTD, and we see the precision, the difference. So we have the whole starting point for the whole instruments together with the 911. And before putting into the water, we calibrate the instruments here.
Yeah.
And when the instruments come back, also we get the point, and without cleaning the instrument, I mean without, and we get the point, what we have, and then we to see what is the difference from the first when we started, and when is to see that it's a drift in the instrument. Yeah.
See, no, Vanessa, I wanted just to ask you, we are in a phase of increasing salinity, but with respect to the past, more ancient data, is salinity increased? I mean, not only from the phase from BIOS, but I mean, when we had before high salinity entrance in the Adriatic, are we now in higher salinity?
High salinity, yes.
Yeah.
Yes,
with respect to the past, I mean,
yes. If we see the Hofmüller diagram that we have for the cruises from 85 till now, we are in a high salinity phase. Although maybe now it's getting a little bit, seems to be changing.
Yeah, but what is the explanation of the increase of salinity?
Well, we have in the more
long-term increase. Long-term, yes.
Yeah, the low frequency signal of
the low frequency maybe is can be described of what is happening in the Levantine. We have to search for what is happening in the Levantine.
I mean, temperature increase, or?
Well, the temperature is the temperature correspect is increasing.
I mean, evaporation increase.
But can I just, there was a paper, I think a few years ago, where Schroeder et al. They published a paper on the long-term increase of salinity in Sicily Strait.
Yeah,
you know that. So there is kind of a general trend of increase of salinity over the entire.
Yeah, I know this, but I'm asking for what are the hypotheses on the basis of this. I mean, is the temperature increase and evaporation in the Levantine basin?
Oh, you mean what
is the driver of this?
It seems that there is less. I heard in one of the hypotheses is the E minus P is getting higher. I mean, the precipitation is we are less precipitation, and also we are less precipitation, less driven runoff. So the evaporation is the principal this main factor.
And the Suez Channel has been doubled since 2017. In August 2017,
Pardon?
the Suez Channel has been doubled. So I imagine that also the input of Indo-Pacific water that is salter than the Mediterranean waters is increasing in the last year. But of course.
We have to see this in the long term, what will happen with the Suez Channel. It already was said that in the Suez Channel that one of the things was about this, that when the dam was constructed, they're getting a little bit more salinification of the basin. But the general trend is to go for increasing the temperature and solidification.
Because in this, I understood that the high salinity core came from this change of circulation.
Yes.
So you need a cyclone on the Ionian Sea.
See.
So there is a periodicity on the formation of this cyclone. We don't see that on 10 years time series. We just see
Because-
one.
Well, we
You
see
don't see
it's
the period of
changing.
this
Yeah.
mechanism.
We don't have
This is
here
decadal.
still.
It's
It's
decadal
more or less
longer.
decadal.
Yes.
Yeah.
Okay.
To
We
7
do
to
see-
10.
We do see it because we have time series of the Adriatic, which are like a 30-year long, so.
Okay.
Obviously not from the fixed point, but we have the number of cruises.
Okay.
So we have quite a long time series where we have seen like 3 cycles of the inversion of the circulation in the Ionian Sea.
The last one, Valentina? Yeah.
It's very well already because you are a bit fast for me. But
That was fun.
apparently the bios changed direction after the winter of 2012.
Well, here we don't have exactly data. That's what I would say. I put it here in the middle. But we'll say 2011. There was more 2012. What was the change of circulation? But you have to know also that the change is not that like goes from one side and goes then to the other side.
I was
It's just
thinking only from the fact that I remember that that winter in 2012 was the famous
yes.
very cold winter for us.
But that was
So
more.
any relation with the formation of high amount of this water or?
This was a different things, but they were because in the Adriatic Sea, the maximum water formation was that took place in the north, in the northern basin. Was in the northern
Yeah,
basin,
but
not
Vanessa,
the southern.
you see, for example, the 2012, you can see that this vertically mixed, the water column is completely vertically mixed with respect to
Yes.
either on one side and on the other.
It's much more.
Yeah, but that was after the decade. That's what I'm saying. There is not. We competed the heat fluxes either in the northern basin. There was a paper from this basin, Benzi et al. 2014, that where we work and we calculated both areas, the northern Adriatic and the southern Adriatic. So the heat fluxes, the heat loss was most intense in the northern, 2 times higher in the north. Shallow part than in the south. Being shallow and more cold water, there was one of them made a huge amount of dense water was flowing down and having the cascaded through the canyon. No, in this case. But, okay, I have to Laura.
Yes.
Okay.
Please.
Thank you. The next presentation is. Sì, no, chiudere,
Ma un po' di ossigeno.
sì, ma chiudere anche quello con calma.
E siamo troppi. Usciamo la metà dentro via.
Thank you. Directly?
Una variante. No, veramente triste.
Dai, non ti frega.
Ma no, ma è incredibile.
Porta fuori il filmato.
Allora non ho capito chi presenta da voi due, perché siete...
Facciamo insieme.
Facciamo a due voci.
Facciamo anche voci.
A quattro mani.
A 4 mani.
Lento?
Che lingua è questo Belzino?
Penso turco.
Turco, probabilmente sì. Se non hanno dato la presentazione,
Non possono
se
presentare.
non avete dato la presentazione non potete presentare. Oh.
L'abbiamo aggiornata.
Andiamo a pranzo prima.
Ma Miro, poi si sono a mangiare.
No, io sono...
Vabbè, ma in questi tempi.
Effettivamente a 4 mani.
Guarda che bel logo che hanno loro.
Ma è sempre Leone, dai. No?
Ma perché Verdi aveva fatto 2 tonalità di blu? Avrei fatto 2 tonalità di blu.
Okay, please, we will resume, start.
We will try
Questo
to
verde marcio.
be quick.
Sì, verde.
Don't you like our logo?
No.
Che tonalità di blu?
Next time we will try
Verde
to make it better. So,
Bravo.
Stefano and I are part of the marine modeling group, together also with Leslie. She's here. She's also from Mexico. And today we are going to talk about the physical and biochemical modeling in the Southern Adriatic Sea. We will give some example of some applications. And marine, quickly, just to see if there is a space for future collaborations or future interests. Who we are. The marine modeling group deals with models we use, and we have different kind of models, hydrodynamic models and food web models, individual based population dynamics, and dispersion and bioaccumulation models. And we work at different, moving in different areas and at different spatial scales. We go from the Mediterranean scale to the smaller basin scale. Here, for example, we have a zoom on this part in the Sicilian Channel, and on the top, a small lagoon that is the Marano Lagrado Lagoon that is located here in this region. And here is a list of recent projects that we were developing, we were involved in, and this project address different area, and we use different kind of models in order to address different questions. Here we have an example of a finite element model grid that is quite useful to be applied in smaller spatial domains, such as lagoons, for example, and especially where the bathymetry is very shallow, or where we have also wet and dry problems to resolve. And we use mainly three kinds of hydrodynamic model: the MIT-GCM, the OPA-TM, and the SHIFM. OPA-TM, I think, derives from Nemo.
Yes, it's the tracer model.
It's a tracer model from Nemo. And here is an example of applications of bioenergetic and metabolic models. One that we developed for the mussels, the other one that we developed for the clams, and for Sparus aurata, in order to address the sustainability of farming of these species in lagoons and in the sea. Here is an example of a food web model. Food web models can be used in order to address the impacts of natural or anthropogenic variations on the food web, including fisheries. We also use couple models, for example, coupling hydrodynamic and biogeochemical models, and we perform statistical analysis such as classification, ordination, and gradient analysis in order to address the trophic structure in the sea environment, or to apply habitat suitability models. And last example, this is one of the projects that have been developed merging different kinds of models. Here we have used hydrodynamic data and hydrodynamic models merged to biogeochemical model, biogeochemical model that was used to simulate the effect of different harvesting strategy of mussels in the Gulf of Trieste. So changing the harvesting density and changing also the environmental factors, we address the sustainability of this activity in the Gulf of Trieste. Now we have
Yes, one application centered on the Adriatic and the Southern Adriatic. We already saw some preliminary results of the study, which was a study we made also with Vanessa, Manuel, and the group of experimental data. So these are the consequences, the effects of this famous Bora event of 2012 that happened in the Northern Adriatic. So just a few words about the Bora, but we already said something. It's well, we had this event, so a very strong, long-lasting event of Bora that lasted for almost 20 days with a very strong gust and a few precipitation. So a very huge formation of dense water. So very cold and very salty, and there was also a low river discharge. So a very small input of fresh water. The Bora blows mainly from these four main, we say doors, le porte della Bora, the doors which are valleys in the Dinaric Alps in these mountains here. So it channels and increases velocity. It's a katabatic wind, so it comes from the mountains, let's say, and falls down to the wind, increasing its energy, its velocity. So this is another example of how was the situation in that period. We see that there was a clear sky because the wind cleared up all the windows. So it's an episode of clear Bora, which we can also have a dark Bora when it rains, when it's a low pressure system. And but in this case, there was really clear sky condition. So we already mentioned this episode in a time series of heat fluxes. If we focus on the northern part of the Adriatic, we can see that there was a very low, a very strong heat loss on the northern part of the basin, which caused this very big amount of very cold and dense waters. The importance of weather forecast, we were planning to do a party for our handball team in that period, and we said, okay, let's make it on the 10th of February. We decided a couple of months before, and it was exactly during the peak. You see, the 10th of February, the peak of Boris is 20 meters per second. We had gusts of more than 100 kilometers per hour. And so we made it 2 months later because there was not the... And these were the consequences in Trieste. So it was very an amazing, very strong event. So, okay, we already mentioned the instruments in the Southern Adriatic, so I skip on this slide here. And also the main characteristic of this time series in terms of temperature and salinity. We were interested in this linear trends, both in temperature in the bottom and in salinity. So it was 0.05 degrees per year and 0.04 units of salinity per year. And then there was this relevant drop in temperature and salinity due to the cascading of dense water.
But the scale is one over the other, it's okay, or is 12, February 12th, February 12th.
Yeah,
it's not over below 12, February 12th.
No, they should be
almost. No, it's not.
Yes, yeah, they are on the same time scale.
Oh,
Yes,
okay.
the cascading is here.
Yeah.
Okay, so we set up this numerical model made of, let's say, 3 models nested one into the other. So a lower resolution of the Ionian and Adriatic Sea, then a medium resolution of the Adriatic, and then a high resolution focused on the Southern Adriatic pit. We, as Vanessa already mentioned, we call this process as an alternation of 2 main phases. So a phase A, this linear decrease. In this case, there is potential density. There was an increase of temperature, an increase of salinity, but the main signal was due to temperature. So we have a decrease in potential density. So we called it phase A, and then the cascading of dense water increased abruptly the density. So we call this phase B. And we wanted to know the causes of this process. So we exclude instrumental drift because of all the reasons we mentioned before. There was no deep convection, no external sources of like some major volcanoes or some kind of stuff. So we ascribe this process to mixing. In a few words, the structure, as we saw before, we see there's the permanent cyclonic circulation with domain of isopycnal structures. And so our hypothesis is that in this closed area, so below the sill, the system is, let's say, isolated. And so it is a continuous mixing of water, and mesoscale and submesoscale structure bring the lighter water from the periphery of the gyre to the middle. And so this is a continuous and very slow increase of density. Let's see if the movie start now. I should make it start from here. And this one shows how the process goes. So there is a, let's say, we call it doming, but I mean, it's not a perfect dome, of course, because there is lots of instabilities and the changing of the main cyclonic structure. But these thermaline structures continue to mix in time. And if we go further on, you see the density has decreased in a very relevant way. And afterwards, you see there is this cascading of dense water coming from here. Oops. Coming from above. And so this dense water fills again the pit, and so the situation starts again from.
Can I make a question?
Yep.
Sorry. But so you consider the decrease of density, the interannual decrease of density, an internal process of Southern Adriatic?
Yes, yes. That was our hypothesis. It was just a mixing process. And so the lighter water from the periphery of the dome was brought to the inner part of the domain by mixing and in fact, well, I can skip on this picture, but this is the explanation of the trend. So in the last 200 meters of water column, this is time and depth. This is the potential temperature trend in time, and this is the advective term, and this is the diffusive term. So all the trend of temperature is explained by advection and not diffusion, not vertical or horizontal diffusion. So that was, let's say, a sort of confirmation of our hypothesis of this kind of mixing process. And so we see in time, so on long time series, this trend seems to be occurring many times, and now we have to check with the new data what is happening if this kind of behavior is still going on. So in density, you see decrease, decrease, and decrease. Okay, so well, I skip on the conclusion since we're running out of time. Just a few words about carbon sequestration and carbon fluxes in the North Adriatic. The Adriatic is known as a sink of carbon. So yeah, just a small cartoon. We have estimates of carbon sequestration for the Mediterranean, but there is a gap of knowledge for the Adriatic. So with this kind of model, coupled physical and biochemical model, we try to do these estimates of carbon sequestration. So the process is the continental shelf pump, which is due to two main processes, solubility pumps, a more physical process, and the biological pump. I'm not a biologist, so in case I say something wrong, maybe Michael or other colleagues will correct me. Anyway, the dense water, I mean, cold winter and dense water, and production of dense water brings the carbon in form of organic matter down to the bottom, and so it sequestrates the carbon dissolved and an organic one to the bottom of the sea. The Northern Adriatic is a typical area for this kind of process because it has strong seasonal variability. So during winter, there is an absorption of carbon, and during summer, there is a decasification, let's say. And also there's a lot of production due to the contribution from the river and water here. So it's a very peculiar site for this kind of process. We studied it with a couple physical and biochemical model, but I skip on these details maybe if we have time later. And so these are an estimate of carbon sequestration, so the carbon fluxes from the atmosphere to the seawater. And there is the variability also of this process during the year. So we have higher values during the cold season and below zero in the summertime. So the estimate was of carbon flux was this one, so 0.46 teragram of carbon per year. Let's say it is an hotspot of carbon sequestration for the Mediterranean area, but I mean, it's just less than 1% of the anthropogenic CO2 emitted by human activity. So it is quite important for the Mediterranean Sea, but if we want to make a carbon budget, let's say that the contribution of the Northern Adriatic is very small. And this plot shows in a vertical section how these carbon-rich waters are exported and brought down to to the lowest layer of the basin. But since we are running out of time, I skip. Sorry, but we don't have we don't have a lot of time. Yeah, just one thing about how things can change during different winter times. So an average winter situation, sorry, this is a warm winter situation, so relatively warm winter. This is a normal winter, so heat losses which are almost the average compared to the climatology. And for example, the winter of 2012, which has been very, very cold. And due to this different kind of winter situation, we have different sequestration of carbon. And so here we see the anomaly of heat fluxes, so positive anomaly, so warm winter, let's say a slightly positive anomaly, so let's say a normal winter, and a very cold winter with a strong negative anomaly of heat flux.
The heat flux you calculated, you get it from era interim or from where? You
from I think from a higher resolution model. Yes, in the WF Marotti era interim was a high resolution data set, I think.
Okay.
I don't remember at the time, but it was higher than the 80 kilometers of the era interim, which are not enough for this kind of application. And also dense water production this is the let's say gives an overview of the dense water. So water denser than a threshold of 29.13. So you see on the normal you have some vein of dense water going down to the Southern Adriatic. In a warm scenario, we don't have such a big dense water production. In a cold scenario, instead, we have a strong vein and a big filling of the Southern Adriatic. Just to see, let's say, we can see that a warm year can have a positive feedback on global warming, on climate change. So we have less carbon sequestration, and so the situation gets worse. And instead, with a cold year, we have more sequestration, so less carbon, and we have, let's say, a negative feedback on climate change, but a positive effect for us, let's say. Okay, just a brief summary of what we did, but I think that I can go on with okay. So well, we studied the CO2. I don't know what's the time. I don't know what's the time. So we said that this Adriatic shelf is an efficient area for CO2 sink, and there is a strong seasonal cycle. So we have to be very careful about how the situation changes during the years. It's a site of dense water production, so it is an important role for sequestrating the carbon. And of course, it is a strong internal variability, so it impacts the carbon sequestration during different years. So now, I need to stay.
No, but I think that if there are questions, maybe you can answer now.
Okay.
Before going to another.
Because there are two different.
We still have 20 minutes left, so.
Can I ask?
Yes.
Che prima?
No.
Vai.
Go ahead.
Yes, first.
Okay,
Yes, first.
Guest from Croatia, Mir.
You said that there is this long-term decrease of the salinity at the bottom layer of the South Adriatic pit, and then we always this what you call step.
Yes.
So that means that there is no ventilation to the bottom layer.
No, until it is. I mean, the dense water cascading is the only way of ventilating.
So the consequence of that could be that there should be during the whole phase the decrease of the oxygen.
Yes, we observed it on the data, but there were some gaps for some periods, and I mean this smoothing doesn't measure the oxygen concentration, but we saw this decrease in time in many different steps during different years when there were available data. We collected the data from the NLDC from the data set.
Because 5 years not ventilation seems to be very long period.
We have some. I have some plots. Maybe I will send you.
Should be
there is this clear signal of decrease.
No, but
No, the mixing mechanism and this cyclonic eddy circulation on the bottom, is this the eddy barotropic or just on the bottom?
No, it's barotropic.
It gets the surface from bottom.
This is a, let's say, bathymetry constrained eddy. It's not a really mesoscale eddy. It's a really cyclonic structure due to topographic constraint.
Okay.
So we are in the middle of the pit, and the circulation goes like this because of dystrophic equilibrium in this closed domain.
And did you measure this is modeling?
Yeah, these are models.
So do you have the vertical velocity? Because the non-hydrostatic might be
yes.
that you solve the equation for vertical velocity. Did you check the distribution of vertical velocity in this?
I didn't check the patches as you did, but I could try to do so because it's an interesting.
Because can be like a convergence on the bottom and upwelling in the center of the eddy. So maybe there is some
Just technical question. If someone have the car un Q3, una macchina Q3.
Q3.
No.
Che macchina è?
No, let's go ahead. No, he was speaking, sorry.
Well, this part
I followed the theory by Mike Spoll. He did this kind of approach with a laboratory experiment and modeling experiment of these eddies carrying the properties from the periphery to the middle of the jar. I can give you the reference to this paper, but these are different approaches which are both quite interesting. So I will check the vertical velocities, how they behave.
Stefan, I wanted to ask you if you can go one of the first slides where you compare the heat fluxes for the different years. Because it seems that in 2012, one of the first, one of the first.
Yeah.
No, there was this.
Where you compare the time series of heat fluxes, it's the beginning of your.
Okay, for the physical part.
Yes.
One there.
Questo qua.
No, sì.
Yes, because yes, in the upper part is a normalized heat fluxes. I don't understand. In 2012, it doesn't seem so strong with respect to 2000 other periods.
But it also being divided into monthly data.
I mean,
so
the average upper.
I can explain if it's under my figure.
No, yes.
Anyway,
it seems a little bit in contrast with the last one.
Because this if you see the monthly data, which is the same. This is average all in the whole winter period. But if you check on the winter data, you see this one is the February event, and so the big. I mean, it lasted for 20 years, so it was very short in time. 20 days. So it's very short in time, very short time period.
Yeah, but the upper part is averaged on which scale? The upper part. No, on the upper graph, the graph number A.
Okay.
On which scale is averaged this?
This is normal. This is the first is normalized for 10 years. 10 years is for the 91 to 2012.
But for the winter.
There is for the whole winter is normalized for the whole period, and it considers that December to March, which are after that are divided for November because we are taking into consideration. We took into consideration the preconditioning.
So this is meaning that the winter on average was not so cold, but only some months was extremely cold.
This one was extremely cold. Yes.
Yes.
Sorry.
And it was because
I admit that I didn't read your paper about the model in the Southern Adriatic. I apologize for this. But I have a question that maybe is stupid because I didn't read your paper. You consider the decrease, the pluriannual decrease of density at the bottom, and you explain with the second circulation.
Yes.
In which way you explain, if you can, explain the increase, pluriannual increase of the density? Because we know that the density go down and then go up also.
But then in the last CTD, the bottom one, we saw just a decrease.
Your model work only for the
We
last.
we studied only that period, and so we don't know if there have been measurements of increasing density, because in theory this process should work only with decreasing density, because you mix water with lighter water which stands above the measurement. So I don't know if measurements.
No, if you close the autumn strait, of course.
Yeah.
You cannot consider the variability of the water, the upper layers, pluriannual.
Mm-hmm.
So it's difficult to understand how the density can increase. But if you run the model only in the period where the density decrease, okay.
Yeah, we study only that period, but
Okay.
we can make it longer. If we will have all the data and we can run.
So it's
simulation.
difficult to think about internal processes that increase the density.
Yes. But it seems from this theory that the only mechanism is the dense water cascading. So abrupt increase and slow decrease.
Okay.
That's the only meaning of enhancing the density
from the north.
is from the north and dense
Okay.
water going down. Yes.
Okay.
So I think that we can go on.
What's the mean heat flux of these Bora events, the negative heat flux, like
I don't remember
What?
the budget.
What you said? What is
like a typical
The back-
negative heat flux for these Bora passages?
If we say happening, for example, in that we have a heat loss of about 800 watts per meter square.
800.
Yes. And normally we said a mild winter we have to 200,
Look at it.
and a normal goes to 600, and then you have the events goes up to 800,000 watts per meter square heat loss. Yeah.
In the Gulf of Mexico with the Northeast, we get some punctual ones of 500.
No, this
But
is
because
normal.
it's very
Yeah.
warm, also the water
Yeah.
and
Yeah, we are. This is very dry, and in this case, the component that you have the latent heat is one of the main drivers, because it's the wind. It's the wind is what is the main, and also we have the sensible heat flux component because of the difference of seawater and the temperature, air temperature.
Yeah, in this case, it was a record-breaking density, but not temperature. So it was a very strong increase of salinity due to evaporation, but the temperature was very strong, but not the strongest ever measured.
But for the strong Bora event, the heat loss is like on the order of 700-800 watts per meter square. This is what we found in extreme.
Yes.
And I repeated it.
I already.
I will repeat it.
Okay.
Because I didn't hear. I don't hear all the time.
Yeah, that's the
And that's one question for you about this modeling, the modeling of the ecosystem.
Yes.
You're using a differential partial equations to model the plankton and zooplankton, or are you doing that? It's a 3D, you're expecting, or it's a 0D ecological model?
Full coupled models.
It's a 3D.
Yes, and yes, full coupled models. We use the 0D models for the bioenergetic models for the simulation of the mussel farming. In that case, we simulated in a 0D the places where you have farming, and we coupled it offline with the biochemical model that was fully coupled with the aerodynamic model.
What is the physical model forced with in the lagoon?
The physical model for the Gulf of Trieste.
No, in the lagoon. The physical model was you run also the ecological model, ecosystem model in the lagoon.
Yes, in the lagoon of Marano, for example.
Yeah, what
Yes.
was the physical forcing for the physical model?
Physical forcing for the physical model are wind, the heat fluxes, and the flood cover, and air temperature.
Boundary conditions you have.
Boundary conditions, yes, we have the open boundary conditions at the sea, for example, sea levels and temperature, salinity, of course, and nutrient if we simulate the chemistry in the lagoons. So besides,
Yeah, please.
Yeah,
if not, we
but
will finish.
this is very, very quick. We will give two examples of applications that of work that we are involved in the last couple of years, addressing the blue growth and the sustainability. Because as our president said yesterday, we do science, we do measurements, and our aim is understanding the processes that we are studying, but also to use this knowledge to inform policy and management in order to obtain to improve the sustainability of the management. And this application is in oil spill. The blue growth strategy is a long-term strategy that was recently introduced in the European Union in order to obtain the goal of the sustainable growth in the maritime and marine sectors. And this means that the European Union wants to push all these activities that are depicted here. And in order to push them in a sustainable way, science needs to inform the policymakers on which are the risks and which are the limits and constraints that should be set in order and when developing this activity. And one of the activities that we recently performed is oil spill modeling. This work was developed on one side for the WWF and on the other side for the Ministry of the Economic Development. And so this is a clear example of how scientific information and knowledge can support the environmental perspective and objectives, and also the economic development that should be framed by the sustainable uses of the resources. And our activity was developed using the MLTGCM model for the REACT-C as a dynamic model, and we coupled on it a noise spill module. And before coupling and choosing the model, we made a kind of selection among the available ones, and we tested 3 of them, and at the end we further developed the oil trans module, adding also additional processes. Again, this is the domain, the hydrodynamic model domain, and with the high resolution nesting for the northern part. We tested 2 different models dealing with different transformation formulations. One of them was more conservative. That means that underestimate the degradation of oil and keeps the oil in the water for a longer time. And then is a model that is more conservative. That means that gives you information that is more use a precautionary approach. And here you can see a couple of simulations of the dispersion of oil released in a certain point. And in the top we can see the time, and due to the hydrodynamic, the oil changes its forms, and
a specific wind field.
We have the specific wind fields, yes.
Well, what was the wind field?
In this case,
Was calm at the beginning and then some feeble bore or
I
something.
don't remember because we
September,
made
wasn't it?
several simulations. I don't remember all of them.
How many hours? I haven't seen how many hours.
This is for 10 days, I think.
10 days.
Yes,
10
from the
days.
16th to the 26th. And so, but the idea is that with this model you can make a single scenario like this, or using another model you can make single scenarios that is more or less conservative, or you can do a 1 year long simulation, for example, discharging oil every day, and in order to map which are the sites that are reached more often, and in this way you can drive probability maps that can be used to support the management authority in order to see if one site is, for example, risky for the environment. For example, if there are some vulnerable sites or sites that are particularly relevant for human activities or from a natural point of view. And so using this kind of models and performing a statistical approach, that means that making 10 years of simulation and making statistics on the results, what we can derive are hazard maps and risk maps, for example, like the one that we made for the Sicilian coast. Here we merged the modeling results on sensitivity index, environmental sensitivity index. And in this way, the sum of them gives us the risk index for each trait of cost. Here we have 4 maps because the simulations were developed for 10 years in each season. So we have a map for the spring-like configuration, summer-like configuration, and so on. Because releasing oil from these sites located in the Sicilian Channel, due to the meteorological forcing to the current conditions, in each season we have a different configuration pattern of the oil stranded at the coast. So we can provide an hazard map for the oil that reaches the coast at each season and overlap it with the sensitivity index and derive a seasonal risk map. Last and very quick application is the one that we did in the frame of the Mantis project. It is a project developed and will end next year in the Adriatic Sea, for the Adriatic Sea, and in order to address the fisheries in the Adriatic Sea and in the Sicilian Channel. We, as a group, focused on the Adriatic Sea. And again, we used the dynamic model coupled to a larval dispersal model in order to, I think I missed one slide, but I will tell you, in order to see how effective are fishery closures in respect to the fishery recruitment. Because we simulated the dispersal of larvae released from the oil basin, and then we can see which are the sites that receive more larvae, and which are the sites that are bigger donors. In this way, the management authority can decide, can be informed to decide which are the sites that is better to close to the fishery. I don't know if what we did. We, for example, here for the nephrops, that is scampo, we simulated the behavior of the larvae that were released from these sites where we know from measurements that the adult live. And we released the larvae during the biological period, that is from in December and in January. And we made a model to simulate the larval behavior and growth up to the moment when the larva reaches the site when it can settle and become an adult. This is a sedentary species, so it's kind of work that can be done for this species because the larval period lasts only for 2 months. And we use also a map of the sediment because the larvae can settle only where the sediment is suitable. And then we run the model. So we simulated the release of larvae from where the adults live. They go up, they make the vertical migration. They can live between 3 and 8 weeks, depending on the temperature that they find in the environment. So the model is also related to environmental conditions. And then when they reach a certain growth, that is, they reach in the time depending on the environmental conditions, then they go up, down, and start to search for the sediment, the suitable sediment. If they don't find the suitable sediment within 5-10 days, they die. And also, if they meet a temperature that is not suitable for them, they die. Facciamo insieme.
Excuse me, Donata, what was the range depth for this particular scenario?
Yeah, it's the depth, both the central and northern area. So there was a map where the adult lived. So they, now you can see. Here we have the larvae that have been released from the adult. And then they are blue, so they are migrating in the Adriatic. When the red ones means that they reached a not suitable site and they die. And
Scampi.
Ma noi va
Adesso.
Pomo.
Perché non è l'uomo?
sì, sì.
When they reach the critical size.
Se
The green is the adult.
How do you fit the model? I mean, where do you find information on the larva, on Nephrops larva? Because I knowledge which is not very related to the captive larva, but quite familiar with the sediment. I don't have no mention about the behaviors of megalopa or other stadium of Nephrops larvae.
Yes,
we have a lot of information on subadult, adults, recruits in general from fishery data, fishery dependent data, fishery independent data from HITS or whatever. Also, there is a project I collaborated with the ex-ISMA EOP now, Ancona, people from Ancona works with Nephrops vegetables, but I don't know, for example, I mean, I'm not familiar with the direct vertical migration of Nephrops larvae, for example. Where does this information come from?
Yes, this information, at first we didn't review the direct vertical migration, but then we were criticized during the meeting and they said, I think Carlo or others, that we had to introduce it. And then we found a master thesis from Smith, I can give you. And they made a lot of measurements on larval migration and related also to different environmental conditions. And so we introduced them in the easier way, I think, just taking the average number. So because the diamortization is connected to the tidal cycle, but also to tidal amplitude and so on. So we skip the tidal amplitude.
So it's quite complicated.
So the idea was to take to take the information available and to take then the simpler ones, because we could not include, for example, the tide, because we don't have tide in the models, but we included the information on the sediment suitability. Because
Include the moon?
no, we did not include the moon. But we can, yes, we
Molto
can.
romantico, non è romantico.
I have some questions about the Lagrangian transport model that you're using. Are you just setting the particles on the first measure depth? Can they propagate vertically too? You're including the vertical velocity also. But when you show the maps of oil spill, this is only the flow.
Oil spill
only the
is only surface.
that it's on the surface,
Yes.
but there are components that are on the bottom of the oil.
Some
There are
models
several
compute
densities.
separately the parts that goes on the bottom, but the part of the oil spill models track only the surface, because the oil companies are mainly interested in the
What
surface.
we see.
In what we see. We aim to improve our model, that is the oil trans model, in order to include also the vertical migration of oil.
And did you put random walk on the Lagrangian transport model, and you add a stochastic? Yeah.
Yes.
Yes, I wanted to ask you on the risk assessment of oil in the Sicily channel. What was the sources that you consider? The offshore platform, or
Yes,
or the oil spill from ships and from traffic, or the combined of
No.
the two?
That was a study developed for the WWF that was interested in making simulations for 6 exploration sites. So there are not only one is a platform, that is this one in front of Gela. The others are exploration sites. They wanted to see if there will be an accident during a future operational activity.
So this is not a combined, of all the potential sources.
No, it's not a combination of all the potential sources.
So it's a minimal risk assessment.
This is really related only to these 6 release points that are located inside the exploration or production in this case.
These are long-term sources with respect to the maritime accident, which are
The first
shorter.
one was the first example was an example of maritime accident.
No, but indeed the oil spill, from platform is not continuously releasing, so it's not. It's the same case. It's only in accident.
In Gulf of Mexico, it was for long-term.
Yeah, but in accidents.
It was a very big accident. But in this case, the aim was to derive a risk map and so
To find the more risky location.
location. Yeah.
Did you do some validation? Validation on the
On the oil? We
drifters. I mean, you're doing virtual particles, so to compare.
not yet, but it would be very interesting to do it in field on blazing.
And the last is the causes because is NBA.
So sorry,
And the last is the causes because
all blazes can be risky.
What is your result? Not really.
because I don't see.
No, I don't have all the results here, but I can show you. From among these 6, some of them are more risky than others, and depending also on the season.
I'm sorry, we have to keep it
This is the last one
Yeah,
we
okay.
can finish.
And then
The
no, we will have lunch.
Yes, at the end for the one after. using the connectivity models, you can compute the settling density, but also different indexes. For example, the retention rate tells you which are the area that retain more than they give. And in the other case here, you can see which are the area that disperse further their larvae. So basing on this information, management can be informed. And the next one, again, you can also write graphs that, depending on what you are drawing, can show you the connectivity between different areas. Here, for example, the colors are related to the colors of these areas, and the fluxes, the dimension of the arrows are the fluxes. You can see which are the fluxes that are bigger and which are the areas that have a higher retention and so on.
Excuse me, because it's difficult to read the graph for me. Relating to the Jabuco Pomo pit, which is in the middle, the red area, which is the connection between the Pomo pit, which is a FRA actually, a fishery restricted area. I don't know if based on these results or it was.
What we can say on the Pomo pit?
The relationship between the Pomo pit and the red area, for example, because in the area in front of Ancona, fishermen fish very, very big novel lobster. So
in this area here,
the population related or not?
Yes.
No, upper. In front of Ancona.
In front of Ancona. Here, yes. So the question is, how is related this area with this one?
Jabuco Pomo pit, for example.
Yes, there is a connection.
Because I cannot understand the relationship.
There is a connection between. Don't have the numbers here. Between this one and this area. So there is a strong connection between these two. And in fact, one of the questions of this project was try to understand which is the role of the Jabuca pit and if it's really segregated as it seems, but the results are that it's not segregated and the differences because there are differences between the sample. The individual collected in the Jabuca pit compared to the others, they are smaller. So the hypothesis was that the Jabuca pit was segregated from the other reactive zones. But our models does not confirm this hypothesis, and instead it highlights the connections between the Jabuca pit and all the areas connected.
Okay, thank you.
Thank you.
Thank you for doing that. Unfortunately, and we can have some discussions tomorrow. We can get some ideas and we can discuss this or techniques or issues.
We will move rather talk after lunch.
Since we are running a little bit late and we have time in the afternoon, so rather you will give a talk in the afternoon, okay? Dov'è?
È dentro la cartella canvese che è incagliato. Questa
I try to be very quick, also short, also because I think all of you have already listened to this to the seminar I gave both in Mexico and here at OGS, so I go fast. Just to say why we are studying this item, the vertical migration, because from the series of the DCP, this is the vertical velocity, we found some holes in the time series that were periodic every 24 hours, and so we wanted to understand why we have this feature. The ADCP is the one you saw from the H1 3A that Vanessa Pepe presented before. And also we see this negative velocity before and this red velocity, so upwards velocity after this hole. And from the echo intensity, we calculated the backscattering strength, that is a qualitative measure of what is inside the water column, the particles that are biological, but also can be inorganic particles and all of this. So this data, we use this data also from models, from what concerns the meteo data or for the mixed layer depth and net primary production, coming from reanalysis in the models. And then we use also the biological data from the University of Dubrovnik, from Rade, Garic, and Mirna Batistich, together with other profiles coming from the premises. And this is the backscattering strength for the whole time series starting from 2006, and this is updated for the last period. You can see that there is more backscattering, the strength is higher, always during the spring-summer periods. You can see that is repeated. This is the total backscattering strength, while here you have the diurnal and nocturnal. It is divided from the diurnally from sunrise to sunset, and nocturnal from sunset to sunrise. You can see that along the water column there is more. There are more particles during the night due to this vertical migration in general. Going this maybe to well, let's skip this one because it's too difficult to explain. We have here the monthly mean mixed layer depth and mixed layer depth and primary production. And if you calculate the correlation, we see that on a monthly scale there is a delay of 2 months in the primary production with respect of the deepest mixed layer depth. This is the backscattering strength just 4 layers. This is the monthly mean, and you see that always the backscattering strength is higher in the higher levels, and there are peaks also in correspondence delayed in time with the peaks in the net primary production. This is on the monthly scale. And here is something new I tried to do with the data before the things you have already seen were just published in the paper. Here I calculated for all the velocities, vertical velocities, the timing of these velocities. If you can see here the lines with the sunrise and sunset, the black line, and the velocities are the colors, you can see that all the negative velocity are along the sunrise and the positive velocity are along the sunset. There is some delay here, for example, during the winter or just during this winter 2008, and or some anticipation of this during the late autumn and the winter the same year. It is not exactly the timing of the sunset and sunrise, but the generic behavior is to follow these lines. I put also the new moon and the full moon. If you see these orange lines are the full moon, and you can see that there are some effects of vertical velocity later on due to the moonlight. This is due to the fact that there is, with the full moon, there is more light in the water column. So if the principle is for zooplankton not to be seen from the from the predators is also that they try to go up later on just to stay far from the surface. And here I put just an example of the currents and 254 meters, just to see what is the horizontal currents, the variability of horizontal currents, and just to say that the vertical migration is not so much disturbed by the horizontal movement, horizontal currents. Even if here you can see that the vertical velocity are very high all along the day, but this is due also to this negative heat flux, loss of heat flux due to the wind blowing very strong and so mixing all the water column. Here below, I tried to plot the velocity the same as this plot, but just with respect to the sunset and the sunrise. And you see that it is not really aligned with the sunset and sunrise, as we have already seen here. Well, this case you have, I have already presented, but in few words, the water column is very much, in February 2008, is mixed. There is a vertical velocity. We cannot see any real vertical migration because of this wind event here. The event is just this one. You can see that you have alternation. The real vertical migration is always present here, but then it is destroyed by this mixing, strong wind mixing here, and then again it appears later on. And if you look at the vertical velocity and the backscattering strength just for layers, this is the hour of the day, always the sunrise and sunset, we can see that for what concerns vertical velocity, there is not a strong signal at 65 meters, but it is stronger, going deeper in the water column. And for what concerns backscattering strength, we can see that there are particles in the water column also during the day. Probably zooplankton or phytoplankton, we cannot distinguish between them, and going down during the day it is almost empty at this depth here. And quickly, with the June 2008, you can see that there is a very clear diurnal cycle. With this is the during day, during night, the particles are going. The zooplankton, sorry, is going up and down, but there is not just a single movement of zooplankton. You can see. Maybe you can see here that there are other features that appears in the backscattering strengths that could be related to different species that are moving up and down with different timings and with different depth range. And if we calculate just an exercise, the average backscattering strength and velocity, vertical velocity, for 3 layers at 55 meters, 75 and 100 meters, you can see that, and this is averaged for June 2008, and you can see that this backscattering is relative to sunrise, for example. It is high here, and that corresponds to the main pattern of the vertical migration, but you also see some peaks here that probably are related to other species that perform that are slower and perform a smaller vertical migration. This is a work in progress. We have just to continue this work in the future further on. And finally, I try to apply the method of Pepe Ochoa and these are the vertical velocity. They are, it is the vertical velocity average for the first period along the vertical with respect to sunrise and sunset. You can see that the vertical velocity, the maximum of this vertical velocity is not happens not at the same time at 100 meters and at 250. There is a slight trend, so it happens before sunrise at the shallower depth, then at the deepest depth. These are for the three deployments, and we can see that always the downward vertical velocity is stronger than the vertical velocity. Here you have the lines of the maximum for each of the deployments, always with respect to sunrise and sunset. For what concerns the upwards vertical velocity, the trend is not so much inclined as for the downward.
Excuse me, Laura, but this is the integral situation for all the mooring, or what is this? This is what is?
Yes, it is average for all the deployment for each depth.
Okay.
The average with respect to sunrise and sunset.
Okay.
And finally, I try to calculate the daily average vertical velocity. So the average vertical velocity during the day, average for all the depth, just to see if there is a trend. As we saw that the slope of that the vertical velocity feature was more inclined for the negative velocity than the positive, I try to do this. And if you see here, the vertical velocity average is almost always negative on average. That I would like to compare these results with the traps. Yes, but we can discuss after that. This I have put some question more than answer because I began to work with these things and there are no results. So here we have some questions, but I don't know if you can skip to tomorrow, or we want to relate the carbon flux. There are main questions, big questions that I don't know if we can answer, but we can try to have some answer from the data, from merging all the data we have from biology, chemical, and also sediment traps. That's all.
Thank you, Laura. Quick question? Someone?
I had just one quick question. Maybe you mentioned it before, but do you make a correction for the season where you have sunrise and sunset? Really, like in summertime, we have.
There were the curves.
Yeah, that's why
you saw. Yes.
Sorry, Laura. I remember that Pepe have more tilts.
Yes.
It's because it's deeper the mooring, or
This one can be a reason, but also can be that we have different species, different behaviors. The water column is not so deep.
It's an interesting result between both databases. No?
I want to do it with the other deployments too, to see if there is some difference. This is just very
Conduct the validation of this data by some samples. I mean, you perform some
via biological samples.
Yeah, on a
yes.
24-hour cycle.
No, on the 24-hour cycle, no, but I skipped because I have already.
Difficult because we did a similar work with Roberto and Sarah.
Yeah.
So with that
Yes,
CP data,
but
they had-
with Rade and Edmirna, we had some. Let's
Because some samplings, but it was not designed for this kind of.
No,
Yeah, of
but
course.
it was not.
All of us, we miss some.
Yes. Here
focus
there
on
are
experiment.
there are also there is also the biology. I didn't describe this because I already.
Yeah, also to identify which species are responsible of inverse
Yes.
migration, direct migration, because we have 3 types of
Yes.
vertical migration. So
Well,
it will be interesting to design a focused experiment.
yes, this would be our purpose. If we can find, we can have financial resources. We want to do it. Yes, because always
Now that you work in Ancona in Adriatic Sea, then maybe we can have to
Yes,
join
because we
to
have
work
to
with.
sample during the day and night. It's you have to design it for it, but the results with the sample they had in a station in the southern Adriatic Peak, not close to the A2 and 3A, are we could see a good system. Yes.
But the problem is with this kind of research, when you design this 24-hour sampling, maybe every hour to see this fine migration, the problem is that most of these organisms might not be catchable by standard nets, which we use. We use 1 square meter net with 250 micro mesh. So if they are fast enough, they will escape from the net. So you don't have a really representative sampling for the fastest organisms. For example, this
to integrate different instruments, maybe because you have
Yes,
also
or-
there
yes.
mesopelagic fishes which are
Yes,
impossible
yeah.
to caught by
So if you
a
have
nance net or
yeah, if we have the different frequencies of this instrument, then you can catch different sizes.
Yeah,
and
that's
see.
the
Because these
problem we
mix
have.
of fish are also, you cannot catch them in a representative way.
Yeah.
Also, this krill is also escaping this net, so it's really hard to get them to be able to correlate them in a really representative way. We have this net zooplankton which we can catch, and the other things are escaping, so we can try to compensate in some way.
Okay.
Okay, so thank you very much. Now we will resume at
Facce delle salve regionali immagini.